Hello everyone, welcome back to another competitive programming 1 lesson, and today we're going to talk about topic 5, binary search and bisection. So let's start off, let's play a game. I'm thinking of a number from 0 to 100 inclusive. You try to guess it and I'll tell you whether your guess is too high or too low. How do you figure out my number as quickly as possible? Well, I mean, by the title of the presentation, you can probably reason that it has something to do with binary search, right? And binary search, just to go over it, is basically taking a range of numbers that could possibly be it, and then dividing the range in half every single time we make a guess, right? Because we can use the information that it's too high or too low in order to figure out what my number is, right? So for example, we start with a range, maybe 0 to 100, and you would guess the middle of that range, 50, and I'd tell you, oh, the number I'm thinking of is higher. So this means that if it's higher than 50, then it has to be somewhere in the range 51 to 100, right? Because, you know, all the numbers lower than 50 are also canceled because I told you that the number is higher than 50. Okay, so I guess in the middle. Or you guess in the middle, that'd be 75, right? And here we're doing integer division here, so you can see that even though it's 75.5, so like 151 divided by 2 is 75.5, we're just going to guess 75 here because we can't really have a point of a number. And so you guess 75, and I tell you, oh, the number that I'm thinking of is lower. Okay, cool, so that means we divide the range in half again, because this means that my number is lower than 75, so the only range where my number could be would be between 51 and 74 inclusive. And basically, you just divide in half over and over and over again until you reach a range of exactly one number, which would be the number that I'm thinking of. So in this way, we can guarantee that you find my number in less than 7 or less guesses, no matter what number I pick between 0 and 100. Okay, so we've had like a general concept, right? So in an ordered list of numbers, right, we have from 0 to 100. In order to search for efficiently, all we have to do is to compare to the middle every single time and divide the range in half. So how would we write this in code? So here we can start with our first example. I'm thinking of number between 0 and n this time. You're provided with a guess x function, which will return -1 if my number is lesser, greater than 1 if my number is greater, or 0 if you got it. Return the number that I'm thinking of. So again, we can just use like what we have previously, right? So we start with our lower bound is equal to 0, our higher bound is equal to n, and while like the bound is greater than 1, has size greater than 1, right? So while low is not high. If you think back here, we ended the search when we had the lower bound equal to the higher bound, because then our number could only be in a specific range. So while low is not high, while there are still multiple numbers in the bound, we find the middle number, right? So this is basically taking low plus high all over 2, except that sometimes we might have overflow happening. So we're just going to do high minus low divided by 2 plus low to prevent integer overflow. So if you click on the link here, this would actually take you to a LeetCode question, which makes you guess a number between 0 and some very high number, and if you just do low plus high all over 2, then you might overflow and not get the right number. Now, we have g, right? We guess if this number is the number I'm thinking of. Well, if g equals 0, that means you found it, right? Because if you got the number, then we're going to return 0. So if our guess return 0, then we found it and we just return the number because then that's a number. But if my number is higher, then you set the lower bound is equal to 1 higher than the mid, right? Because you know already that the mid is not going to be it, so you're just going to set it to low is equal to mid plus 1. or else my number is lower, right? If g is equal to -1, my number is lower. So then we set the high to mid -1, right? So we shrink the range the opposite way. And finally, when low equals high, we just return low or high. They're the same number. And that means because the only way that this loop would exit is if low equals high, and if low equals high, then that means our number is going to be within the range. So that was a pretty easy problem. So a little bit more on binary search. So binary search takes O of log n time, which is an improvement on the O of n time that a linear search would take, right? Because every single time we're just dividing the range of numbers by 2 until we have a range of only 1 left. So this means that we can search any list of numbers, actually, any sorted list of numbers in O of log n time instead of O of n. And that's a really huge improvement when you think about it, right? If you have like bounds up to like 10 to the 18, this is actually a very common constraint in competitive programming, because this would be the upper bound for a long integer. So if we are guaranteed log n time, we can easily solve this, right? Because log base 2 of 10 to the 18th is actually a pretty small number compared to 10 to the 18th itself. If we tried to just linearly searching through the entire thing, we would take way too much time and it would just time out, so we wouldn't be able to do it, and binary search would be the only way. Now, binary search works on any sorted list of numbers, right? So the list has to be sorted. If the list is not sorted, then we can't really guarantee when I say that, oh, my number is higher when you guess, then you can't really guarantee that all the numbers lower than that are also higher. So it only works if the list is sorted. Now, if there are multiple of the target elements in a sorted list, binary search is guaranteed to return one of them, but not guaranteed to return a specific one. So what this means is that basically when we're writing this sort of like basic binary search, if we're say searching for the number 6 and there's like 4 6s in the list, we don't know which one it's going to return. Now, C++ has functions, namely lower bound and upper bound, that will either find the first 6 or the last 6, and Python also has a bisect module that will do the same thing. But with this sort of simple binary search that we're currently writing, it's not really possible to find the first or the last one. And finally, binary search can also detect if the element is not in the list. What do I mean by this? So if you think about our original solution to number guessing, we were searching through all numbers from 0 to n, right? So no skips in between. So we can use just while like low is not equal to high. But when there isn't a when there isn't the number in the list, then this will never appear, and we might have it when we like change the bounds like this. We might have it that low is actually low is actually greater than high. So if we just set low is greater than high, then we know that we're never going to find it, because when low is greater than high, then like the bounds are broken. We didn't find anything in between. Now here's a little animation about binary search. I guess this is already in progress, so we're going to wait until it refreshes. But we can sort of see how binary search works now, is that it takes like the middle element and then sort of cuts it off until we find the right element, right? While sequential search just goes one by one. And of course, sequential search will take a much longer time than binary search, because again, sequential search is in O of n time and binary search is in O of log n. Okay, so let's start with example 2, which is just aptly named binary search. Given a sorted array, check if a target value is in the array. If it is, return the index, and if it isn't, return -1. So again, we are just going to use basically the same solution as last time. So first we're provided with a list of numbers and a target number that we're looking for. We set low and high to be encapsulating the entire array, right? This would be the first index, this would be the last index. And while low is less than or equal to high, right? This is going to be a different condition because we know that if low is greater than high, that means that our bounds have broken, then the number is not going to be in the list. So again, we do the same thing. Mid is between low and high, and if num's mid is equal to target, return mid, and etc., etc. We just do the exact same thing as before. The only difference is that we will return a -1, right? The number is not in the list if low is greater than high. So even more about binary search. It seems like a simple concept, right? It's pretty easy to wrap your head around. You just divide the length in half until you find like the number, or you don't find the number, or basically whenever the range is equal to has size 0. But there's like a few small details which you should take note of, right? So for example, which condition do you use? Not equal to, less than or equal to, or just straight less than, right? So what I'm talking about is the condition right here. So if we are guaranteed for that the number is inside the array, then we could just use not equal to. But to be safer, we should just use less than, just to be sure. We can also use less than or equal to if we want to check it when the range is of size 1, right? So here we have it as less than or equal to, so that even when low is equal to high, we will check if mid, or I guess just the number, is equal to the target. But if you think back here, we have if low is not equal to high here, so when low equals high, we just return immediately, right? So again, it's just basically a slight difference in the way that the program performs when we use different conditions for the while loop here. We should also consider an interesting edge case that occurs when the range is size 2 and the target value is not in the list. So this happens because when the range is of size 2, what happens is that low actually turns out to equal mid. So for example, we have this small array here. Let's just assume that the binary search has reduced it down to these two values, and let's just say we were searching for the number 3. Unfortunately, this number isn't in the list, right? So here we have index 0, index 1, index 2. So our low would be index 2, our high would be index 3. Well, guess what happens when we have when we try to calculate mid? 2 plus 3 is 5 divided by 2, interdivision is 2. So it turns out that mid is actually the same as low. And when we find that, well, we're comparing this 4 with, we're searching for 3, right? We're comparing this 4, oh, it's less than, so we gotta set high is equal to mid minus 1. Well, mid minus 1 would be right here. So you end up with a case where low is greater than high. And this is what I've said before when the range breaks down, right? And usually you have to figure out how to handle this. Like sometimes you could say, oh, the range broke. I don't want to care about this anymore. I just return -1 or something because I didn't find the integer. But sometimes you're looking for like the lower bound, right? So you're looking for the greatest number, the greatest number that's less than the target number. Well, then you would need to return the 1. If you were looking for the smallest number greater than the target number, you'd need to return this 4. And so how you handle that may be different depending on how you want to implement it. So if you instead set high equal to mid, you won't have this weird thing happening where low is actually higher than the mid. You will always have low equals mid as your ending condition. Now, you see how there's like so many different ways of doing binary search, and there's not really a perfect way, right? So you can try to like experiment with your own code and see like what works for you, what makes sense to you, and just use that. Or of course, you can just instead of using the binary search that we're doing now, just use the C++ lower upper bound functions, or use a Python bisect module, or use Java, I believe, collections module, etc., etc. So with that in mind, let's just go into our final binary search example, valid perfect square. Given a positive integer n is n a perfect square, you are not allowed to use built-in functions like square root. And this will be between 1 and the maximum long, right? So maximum long is this really huge number, around 9 times 10 to the 18th. And of course, we can't use sequential search here. That would take way too much time. So we could just binary search instead for the answer, setting our high upper limit equal to the square root of long max, right? This turns out to be this number right here, so that will be our upper limit. Here we have, again, yes, our low is going to be 1, our high is going to be this square root of the long max. If num is greater than high times high, right, so we're going to return false. So if our number is greater than the maximum perfect square that it could be, then we're going to return false. And now, while low is less than high, we're going to check if mid is equal to low plus high over 2, like the middle between low and high, and do our normal binary search stuff. So here, we're just going to, again, set high equals mid. Now this will make sure that the loop exits when low is equal to high. So when low is equal to high, we still need to check if that number actually is the like a perfect square or not. So we need to return if like the number itself, right? If the number equals like low times low, then that means it is going to be perfect square. If it's not, then the only element in the range is going to be not a perfect square, and so we can confidently say that num is not a perfect square. But there are, again, different ways of doing this type of binary search as usual. So this, again, would be another solution, right? While low is less than or equal to high this time. So we will still check it inside this loop if low is equal to high. And we change how we shrink the range this time. And this time, we exit the loop when low is greater than high. So this is really, again, a slight difference in the way that we check these numbers. And this finally exits the loop when low is greater than high. So when low is greater than high, the range is broken. So we just return false. We know that there is no number in here. If we ended up with, we are guaranteed that if the number was within the range, then we would have encountered this part, right, sometime in the middle there, and we would have returned true. All right, so finally, we're going to talk about bisection. So binary search isn't just limited to arrays of numbers. We can also apply binary search to like functions, not limited to integers. We can like go into it. And a function is called monotonic if it is strictly increasing or strictly decreasing. And you can sort of think how this would be like the function is sorted, right? It either always goes up or always goes down. So we can do a binary search on it. And when binary search is applied to a function like this, we call it bisection. And sometimes a problem can be solved by translating it to an equation, then solving using bisection. So we're going to go through two examples here. First will be easy, and second will be a bit more involved. So for the example, square root of x, given a positive integer x, without using any built-in functions, calculate the square root of x to plus or minus 0.001 accuracy. Well, we know that square root of x is monotonic because as like our x value increases and the square root value always increases, so we know that we can use bisection on this. So we just start off with low equals 1, high equals x, right? Because we know that the square root of x can't be greater than x if it's greater than 1. And we terminate the search when high minus low is less than or equal to 0.001, right? So because that's how much accuracy we want, this guarantees that either low or high are within 0.001 of the answer. So we just use basically binary search, right? We use doubles now because we're not limited to integers. Low is equal to 1.0, high is equal to num. And while high minus low, right, the difference between high and low is between 0.001, we just take the midpoint. We do our check, right? We just bundle our equals and greater than logic together, because it's really unlikely that we're ever going to have the exact number, especially when we're calculating square roots. So if we just bundle this together, then it doesn't really change the function, and we can just basically write less code. And we just set high is equal to mid and low is equal to if high is equal to mid if it's our number is less than or equal to mid times mid, right? And you can, this is basically the same thing as we had earlier here. And if it's lower, then we just set, if it's higher, then we just set low is equal to mid, and we return high. Now, we can also return low here, but it doesn't really matter because both are within 0.001. And the interesting thing here is that we're actually not going to round, because if we round, then the rounding might bring us to greater than 0.001 error. So we want to keep it just as is. We return the number as is, and this will guarantee that we will return a number within 0.001 of the actual square root. Now, for the more involved example, cookie cutting. You have a circular cookie centered at the origin with radius 1. You want this cookie with a friend who only wants n% of the cookie. However, all of the cookie cutters you can find can only make a single vertical cut. Return the x value plus or minus 0.001, where you should make your cut such that the left side has n% of the cookie and the right side has 1 minus n%. And you can sort of think about this problem in terms of bisection again, right? If we start at the very left side of the cookie, then we cut exactly 0 off, and as we increase the cut, our left side increases, right? So this is going to be monotonic. So how do we find the numbers, though? How do we make a cut such that this part here, for example, is exactly 40%? Well, we can just use calculus. We know that the total area of this circle is pi, right? Because pi r squared, radius is 1, so pi times 1 is equal to pi. So we need to make the cut, which makes the left half have an area of pi times n%, or n over 100. Now, the area of a segment of a circle is just like sort of the area bounded by a chord of the circle. And this can be calculated using the integral from -1 to x, right, or whatever value, of 2 times like the upper half. So this value right here, 1 minus t squared, would be this curve upper half right here. If we take the integral, we're just taking the area underneath, right, from -1 here to whatever x value. And we're taking 2 because we want both the top half and the bottom half. So this integral will allow us to have, will give us the area of the cookie that is to the left of the cut. Now, when we evaluate the integral, we get this following function, the square root of 1 minus x squared times x plus the arcsine of x plus pi over 2, where x is in radians. And we know this function is monotonic because at any point, if we move to the right, we're going to have more area. So we could just binary search on this to find the correct x value. And remember the correct, we want this value here, right? This represents the area to the left of x. We want this to equal pi times n over 100. So again, we just have our function right here, right? So function is what we calculated here. If you want to just calculate the integral yourself, you can for practice. But our cookie cut function, we are going to get some n%. We are targeting this much area, right? Area is equal to math.pi times n over 100. And we set low is equal to -1, high is equal to 1, right? So low is equal to -1 right here. High is equal to 1. Because those are the two ends of the cookie, we have to make a cut between the cookie. And while high minus low is greater than or equal to 0.01, etc., it's basically the same thing as before, except we are comparing the value of the function evaluated at mid to the area. High equals mid, else low equals mid, and return high. So that is going to be it for binary search and bisection. If you have any questions, remember you can just go on Piazza and ask a question, and I'll respond as soon as I see it. Binary search is honestly a pretty simple concept, but it's really important, and it helps you solve a lot of problems that you would not be able to solve without. So the problem sets are mostly designed to get you familiar with binary search, coding binary search. If you want to use like the built-in functions from C++ and Python, feel free to do so. However, personally, when I code, I usually use like what we've covered in class today, just because that I find it's easier to think about when I'm actually typing out the binary search instead of just using a function, but you can do whatever you want. The homework set will consist of 3 problems again, and they let's see, it should be due on July 10th. Again, if you have any questions, remember you can just ask on Piazza, and not much else. Good luck. Have fun.